Peace out. Good morning, everyone. Actually, good afternoon in China. I hope everyone is doing very well. Today, we will finish this part of the thermal transitions of polymers that we have been talking last week and the beginning of this week. Can please the teaching assistant text me to let me know if you can hear me well? And last Thursday we talked mostly about the melting and what essentially is melting and what affects melting. And we said that melting essentially is a temperature at which we destroy any crystalline regions, while crystallization, which we will focus today, is the process where essentially we create those crystalline regions. And as we said, as with everything, it's easier to destroy something than to build something, okay? So a crystallization is a much more complex phenomenon compared to melting, okay? Let me see if I have any notifications from the TAs. No notification. Anyway, I continue talking, and if there is a problem, please text me on Wecom or whatever. So let's go through a quick, brief overview of what we said last time. We said that more materials are completely disordered, so they have only glass transition. Okay, we said that the glass transition is a property of the amorphous phase, while melting and crystallization are temperatures that relate to the crystalline phase, okay? And yes, we said that the glass transition is a second order transition because we have a change of slope in terms of the volume, while in the case of the melting point, we have a change of a significant increase, okay, in volume, in enthalpy, or in entropy, okay? And it is a first order transition. We said that the melting point has very similar characteristics that affect the melting point in relation to the glass transition, okay? So glass transition and melting point are mostly affected by the same parameters, okay? And the same parameters increase or decrease the temperatures of melting or glass formation or glass transition. And we said that melting is given by this equation, okay? Simple equation, the ratio of the enthalpy over the entropy, where essentially the entropy is very important because it tells us how much disorder we have in the system, okay? And the more disorder the system is, the less the melting point is, the lower the melting point of the temperature, okay? These are the parameters very similar to the glass transition temperature. And we said, of course, that because of when we have oriented change, okay, we have lower amount of entropy, and that leads to an increase of the melting point, okay? Because the number of statistical states that are available to polymer chains is much lower compared to an amorphous material or a material where the chains are entangled, okay? Yes, and this is the empirical relationship between glass transition and melting point, okay? These two equations for symmetric and asymmetric chains. I repeat, this is empirical, so it shouldn't be treated as, let's say, absolute truth, but generally it provides a good estimation regarding the temperatures of melting or crystallization or glass transition, sorry, and their relationship, okay? We briefly spoke about the melting, but we will talk in more detail today when we will examine the differential scanning calorimetry method, and we will see how during heating or cooling of a polymer, we observe the different phenomena and how do these appear in a DSC scan, okay? Okay, so let's start talking about crystallization. And we said that crystallization is of very high technological importance, okay? And why is it so important? It is because many materials will crystallize to some extent when the molten polymer is cooled below the melting point. Okay, so in this case, this procedure we can do it repeatedly, and that is very important because polymers are the only materials where we can destroy their crystalline regions by melting, and then we can build them again as many times as we want with little or no effect on the ultimate properties of these materials. Okay, so that is why when we break a polymer, we can remelt it, and then we can reform it. Okay, so that is why it is of very high technological importance. Of course, there are a number of factors that affect the rate and extent of crystallization for a polymer. Okay, and they can be variables such as the cooling rate, the presence of any orientation if they melt, the melting point or the melting temperature, along with factors that have to do with the structure of a polymer, such as the tacticity or the molar mass of the polymer, the chain branching, or the presence of any additives. So as you can realize, crystallization is a very complex process, okay? Crystallization, we said it is a two-step process. It takes place firstly by nucleation and then by growth, okay? And we saw that because the system, you saw in this graph, we generally have the observation in physics of polymers that the system prefers lower Gibbs free energy, okay? Because the system is more thermodynamically stable when the Gibbs free energy is low. So below the melting point, we have the crystalline phase, and above the melting point, we have the liquid phase, okay? Here we have a liquid. So let's talk about the two phases of crystallization, nucleation and growth, okay? So we said here that nucleation is stimulated by intermolecular forces. So when we have intermolecular forces between the chains, we have this certain arrangement of the chain during cooling from the melt, and that takes place at thermal or density fluctuation or impurities and other particles. And that separates nucleation into two types of nucleation, okay? We have homogeneous nucleation, where essentially, in this case, the thermal motion causes subchains or segments of the crystalline polymer to sporadically cluster within a homogeneous phase, okay? And this phase grows nuclei, and nuclei start creating more nuclei, and then we create chains, okay? The homogeneous nucleation is very rare, and it takes place only in case of very pure systems. And very pure systems, essentially what we mean is monodisperse systems, such as some proteins, okay? So if we have a certain amount of dispersity, it is very difficult or almost impossible to achieve, or not almost, it's impossible. So we cannot achieve homogeneous nucleation if we have polydispersed system, which is 99.99% of the times, because the chains are not the same length, okay, or weight or whatever. So there should be one type of chain where we will be missing certain segments. So in this case, heterogeneous nucleation will take place. So in homogeneous nuclease, we have statistical fluctuation in density or in chain conformations, okay? And what do we mean by statistical fluctuation in density? I'm not sure if you've seen this experiment where people put deionized water within a very smooth glass flask, okay? So you have deionized water within a very smooth glass, okay? And you put it in the freezer. when you take it out very slowly and very carefully, the water within the vessel, it is very clean, okay, and it's still liquid, okay, even though it's below 0 degrees. That is because there are no external factors that can initiate nucleation. However, when we quickly shake the bottle like that, then we cause a statistical fluctuation in density, okay? And that leads to crystallization of the water, the formation of ice, okay? So an example for this is the ionized in very smooth glass vessel, and then we use it below 0 degrees Celsius, okay? And then once we move it very, very fast and very abruptly, then we cause this fluctuation in density, and we crystallize the material. Now, heterogeneous nucleation is the most common type of material, and it's generally considered by many as the only process of generation of nuclei. Okay. The heterogeneities in this case are external nuclei of small size. These nuclei are small size, can be, I don't know, from 2 to 10 nanometers, or it can much larger. And it can be the dust that is present in the atmosphere of polymer processing. It can be the walls of the container. It can be any catalytic residues, any residual nuclei present in the polymer melt if we have not completely melt our polymer. Or sometimes we introduce some nucleating agents, okay, in order to speed up crystallization, okay? So if we put some particles within our polymer melt that are solid, okay, when we cool down our material, then nucleation will start in the region where these particles are concentrated, okay? These are generally considered foreign bodies. So sometimes we use nucleation agents, to adjust the time scale of crystallization for production process. As you can realize, and let me explain why we do that. Because if you are a company, okay, if you are an industrial partner, and you want to produce, let's say, a polymeric application, and you know that your polymer crystallizes in, I don't know, it takes 5 minutes to crystallize. But within those 5 minutes, if you reduce the time to half, you can produce twice the amount of polymer, okay? So if you add a certain nucleating agent that can speed up the crystallization process, that can help you produce even more materials. And that is why industry in general prefers heterogeneous nucleation and fast nucleation, okay? Fast crystallization, okay? So nucleation, as we said, we start with small nanometer-sized areas. Usually, these nuclei are in the region between 2 to 10 nano. And in this case, we have some segments that start parallel to each other. So you have segments that start aligning, okay? And then they keep growing because they keep attracting more and more segments, okay? So these seeds, these nanometer-sized areas, they grow further, and the grain size exceeds a certain critical value, and then they form the change, okay? So we have the growth. So here we have a nucleated material. Yes, this is the let's say, definition of the heterogeneous nucleation. So we introduce within the polymer melt impurities, dyes, plasticizer, fillers, so many other inorganic, usually inorganic type of material, but also organic, as we will see in a bit, where, as I repeat, in the presence of these foreign particles, we have heterogeneous nucleation, and heterogeneous nucleation is much faster process, okay, and leads to much faster crystallization, okay? So yeah, this is the process that happens. So we have small molecules, they create disordered regions, and then these are the crystalline regions. Because we have order, okay? So we have both crystalline, and then we, in order to form the semi-crystalline polymers, then there are also regions that are not perfectly crystallized, okay? So what is crystal growth? Essentially is what we said. It is recruiting of chains to the nucleus, okay? And it is in competition with dispersion, as you can realize. So it fully depends. The crystal growth depends on the temperature. Okay. The temperature of crystallization. So, if it depends on the temperature of crystallization, what is the temperature at which crystal growth takes place? Okay, and generally, crystal growth takes place between the glass transition and the melting point. Okay, it takes place for temperatures below the melting point and above the glass transition temperature. So we have glass transition that is a lower temperature than the temperature of crystal growth or crystallization, essentially. It's lower than the melting temperature. And if we want to be slightly more accurate, an approximation of these values is that this temperature of crystallization should be around in the region of the glass transition plus 30 Celsius degrees, okay? Or the crystallization temperature should be in the order of the melting point minus 10 Celsius degrees, okay? So approximately crystallization temperature can be found at 30 degrees above the glass transition temperature, and 10 degrees lower than the melting point. Of course, these are approximation, okay? These are approximate values. But these are expected to be in this region, okay? Crystallization is expected to be within this region, okay? Crystallization as you can realize, if we have a polymer that consists of both crystalline and amorphous regions, then we can consider this polymer as a kind of composite, okay? Where we have the crystalline regions that essentially behave differently compared to the amorphous regions, okay? So they give out different properties to the polymer. So the properties of the polymer are the combination of the properties of the amorphous region and the crystalline regions, okay? Crystallization in general affects the mechanical properties of the polymers and decreases their volume, okay? So you can easily realize that the volume decreases because we have more ordered structure. Okay, so this one is more packed than this one, than the amorphous one. And obviously the mechanical properties are better because this close packing gives higher strength and modulus, okay? Also, besides mechanical properties, I'd say the other properties that are affected are chemical properties as well, or optical properties. So as you can realize, the material with higher crystallinity will have different optical characteristics compared to an amorphous material. And chemical, again, it's kind of what is the resistance, let's say, of a polymer to some chemicals. And when you have more ordered regions, the resistance is much higher, okay? And this is the growth rate, okay? Let me go to nodes and make a graph. Okay, so we are 25th. I will give you these nodes as well onto QM Plus, okay? So if you don't want, there's no need for you to make this graph. So if we look upon the growth rate of isotactic polystyrene, okay, and here in the y-axis we have the growth rate, which is given in terms of micrometers over minutes, and on the x-axis we have the temperature. Okay, let's say in Kelvin this time. So for isotactic polystyrene, we said that this is the growth rate of radius. Okay, so essentially it tells us how fast this radius of growth takes place. And let me make this a bit better. Okay, that's better. So for isotactic polystyrene, if we say this temperature is 390 and this temperature is 510, okay, the growth rate looks like that. Okay, it looks like a bell. Okay, so if we start, we said above this temperature, what is the characteristic temperature that we have? So above 510, what temperature would you expect to see? What thermal transition? Let's say, what important thermal property? Can anyone tell me in Wacom? Above 510, which is the thermal transition that you expect to see? Anyone? Yes, so above 510, we will have the melting temperature, and obviously below 390, we will have the glass transition temperature, okay? So if we start from a temperature above 510, we're in the melt state, okay? And let's now suppose that we're cooling down our polymer, our isotactic polystyrene. What happens when we cool down the isotactic polystyrene? Essentially, we increase the melt viscosity, okay? So if we go in this direction, we have an increase of melt viscosity, okay? And what happens when we increase the melt viscosity because we cool down our polymer? This facilitates formation of nuclei, okay? This makes nucleation to take place. And then we have a further growth of these crystalline regions to the existing nuclei, okay? So we have increase of melt viscosity, and what happens is that facilitates formation, nuclei, and recruitment chains. Okay, so we cool down our polymer, we increase the melt viscosity, we initiate nucleation and growth. Okay, what is growth? Is recruitment of chains to the existing nuclei until we reach that maximum point at a certain temperature. It doesn't really matter. And then from this maximum point, we have a decrease of the growth rate. Okay, why is that? Because the thermal energy that we give to our system, okay, the thermal motion is too small, okay? The thermal energy is too weak to attract, to recruit more chains, okay? So in this region, let me use another color. So here, the thermal energy is too weak, slow to recruit chains. Okay, so the graph of the graph of the growth rate versus temperature will look like a bell. Okay, this Gaussian, let's say, distribution, where when we start from higher temperature, we increase the melt viscosity, and because the melt viscosity is increased, the chains don't move as fast, so it's easier for the polymer to form nuclei and recruit chains to the nuclei. Okay, but then when the thermal energy is too weak, the chains don't move enough. Okay, so if they don't move enough, they don't have enough power, let's say, they don't have enough movement in order to be attached to existing nuclei. Okay, so the growth rate falls significantly when we move away from this maximum temperature. Okay, and when we essentially, what we do is we approach, in this region, we approach glass temperature. Okay, now let's go back to our slides. So as we said on Thursday, we said that the chain regularity affects significantly all the thermal transitions. And of course, the crystallization could not stay away from that. So the different chain regularities lead to different types of let's say, speeds of crystallization and different and different types of crystallization. Okay, so generally, when we have crystallization, we will have these different types of regularities. Okay, we have isotactic materials, where we have the functional groups on the one side of the chain. Okay, syndiotactic regularity. Okay, where we have functional groups on alternating sides of the chain. There is also another type of regularity which is not very common. It is the symmetric type of regularity, where the functional groups are in the same point, both in both let's say regions of the main chain, so above and below the main chain. And also, obviously, we have the random or atactic. Let me use another color. When we have a random chain regularity, as you can realize, generally these materials are amorphous, okay? The crystallization, as you can realize, is favored by a regular arrangement, because what is crystallization is creating order, okay? And in these materials, isotactic, syndiotactic, or symmetric type of materials, we have a high, let's say, a regular arrangement of along the polymer chain, okay? A high degree of order along the polymer chain. So gives this structure a high degree of symmetry. And for example, you can see that in an isotactic and syndiotactic polypropylene, we have in isotactic, we have the side chain, the phenyl group on the one side, or the isotactic, we have it in both sides of the macromolecular chain, perfectly alternating. So they have a melting point, while atactic, where the presence of the phenyl group is in different types of carbons, okay, in different regions. So we don't have a perfectly alternating structure. In this case, we don't have a melting point, okay? So the same applies for polypropylene, okay? This is the second example. So atactic polypropylene is a low melting material, which is amorphous, okay? And also it's highly swelling a lot in liquids. While isotactic polypropylene has a high melting melting point, okay, it's a crystalline material. It is used extensively in a number of industrial applications, okay? The same applies for syndiotactic PP. Now, we said that crystallization in general and the high degree of crystallinity is able to affect significantly some properties of the polymer, and more specifically the mechanical properties. However, we should pay attention to the degree of polymerization with relation to the crystallinity of a polymer. Generally, we said that the crystallinity of a polymer is within the region of 20 to 80%, okay? That is a percentage of crystalline regions within the polymer. That is the most common type, let's say, regions of crystallinity. So, as you can realize, short polymer chains can form crystalline regions much easier than long polymer chains, okay? So it's easier for a chain that is like that to form a crystalline region like that, rather than a chain that is that big to form a region that is like that, okay? Because you can realize the long chains can have a higher degree of entanglement, and it can take more time, and it demands a more stable conditions in order to form these crystalline regions, okay? So high crystallinity generally means stronger material, while when we have a low molecular weight polymers, the low molecular weight means low mechanical properties. So we have a counterbalance of the properties. On the one side, the high crystallinity gives good mechanical properties, but the low molecular weight generally means that we have a material that is initial mechanical properties are not as good, okay? So low molecular weight polymers usually are weaker in strength even if they are crystalline. Okay, and why is that? Because they have a low degree of entanglement. So in this case, the polymer chains can slide each other and cause a break. Okay, so if someone tells you that, okay, my polymer compared to polymers that have a degree of crystallinity, one has a degree of crystallinity of 60% and the other has a degree of crystallinity of 40%, which would you expect to have the better mechanical properties? Then you would say it's not possible to answer if I don't know their molecular weights. Okay, if the polymer with 40% of crystallinity has a much, much higher molecular weight that can give a higher mechanical properties compared to the more crystalline polymer that has a much lower molecular weight, okay? So when fabricating a polymer by controlling its degree of polymerization, we need to keep a balance between the degree of polymerization and the degree of crystallinity in order to achieve good mechanical properties, okay? Now, there are a few different types of crystallization, and a very characteristic type of crystallization that is used in industry in order to create either intricate shapes, such as bottles in this case, or create fibers, is called strain-induced crystallization, okay? There are a number of factors that affect strain crystallization. Let me write these down. I didn't write this down. Factors that affect strain crystallization are: one, the molecular structure; two, of course, the temperature of strain crystallization. By molecular structure, we mean the presence of regular arrangements in the polymer, the presence of a long or a short chain, and the intermolecular forces between the chains. Okay. Temperature, of course, and also the type of deformation that we use. Okay. So when we use strain-induced crystallization or stress-induced crystallization, we arrange the chains next to each other, like when you see here, we have arranged okay, and because the chains are arranged next to each other, we have intermolecular forces between the chains. As we said, when the chains are packed closely to each other, then forces act between the chains, and then we produce stronger materials. Okay, and because these become very closely packed, this enables crystallization. Okay, as you would expect, an oriented crystalline polymer, has a much higher tensile strength than unoriented polymer. It's easy to see that if you have a polymer that is completely amorphous and pull it, then it will stretch out but then break. If you have chains that are oriented like that and you have these crystalline regions here, the yellow ones, okay, these are more difficult to break, and that gives them higher strength. Okay. Now, cold drawing is essentially stretching, and you have both cold or hot drawing. Okay, that is either in the presence of temperature or not. You can have it in a solid material where you pull it a bit and then you arrange the chains, or if you soften it a bit by increasing the temperature and then stretch it a bit, then you make the chains align along the direction of stretch. Okay, so in this direction, strength and modulus are much higher than the undrawn materials. Okay. Now, crystallization rate. Different polymers crystallize in different rates, as you would understand. Okay, and as I said, generally industries prefer to make polymers crystallize faster. And because they want to make polymers crystallize faster, they usually add nucleation agents or stretching or apply stretching. So in the case of polypropylene, polyethylene terephthalate, and so on, they add nucleation agents. So in this case, we have heterogeneous nucleation. To be fair, in the other type of polymers, we also have heterogeneous nucleation, but it's more obvious. Let's say the increase in the rate of crystallization when we have particles such as nucleation agents. Okay. So different polymers. I only want you to remember from this slide that different polymers have different degrees of crystallization, and essentially, when we increase the rate of crystallization through the use of nucleation agents or stretch-induced crystallization, in this case, what we do is affect significantly the final crystallinity of our material. So something very important now is how fast we cool down our melt in order to crystallize it. Okay, because we say in order to induce crystallization, we have a molten polymer. Okay, and then we cool it down in order to create these crystalline regions. If the cooling rate is faster than the crystallization rate, what happens in this case? We do not allow the polymer to create this crystalline region because we cool it very fast. Okay, this process is called quenching. And essentially what happens is we do not okay. In this case, when we have an amorphous product, but the cooling rate is faster than the crystallization rate, essentially we say that we do not allow the chains to induce homogeneous or heterogeneous nucleation, let's say. And in this case, we have different properties for the polymer. In the case of the cooling rate that is lower than the crystallization rate, obviously, we have a normal crystallization. There is enough time for change to form disordered regions. Okay, and in this case, we have a semi-crystalline product. Okay. So essentially, even if it's regular or irregular, it doesn't really matter. And we say that for regular chain polymers, quenching leads to amorphous polymer, okay? Because we don't have enough time to crystallize. Well, slower cooling leads to semi-crystalline polymer. And for irregular chain polymers, we commonly have glaciamorphous polymers, okay, which are completely amorphous. Well, in the case of when we have large regular side chains, in this case, we can also quench them and make them glaciamorphous, or apply slow cooling and get semi-crystalline polymers. Let's take a 10-minute break now, and then we will see what are the structures that are formed during the crystallization process and how we can observe them with a microscope. Okay, 10-minute break, and we will resume with how crystallization takes place. Okay, so let's continue. And let me, okay. Yeah. So let's continue with the crystallization process. And let's have a look how can we observe experimentally the crystallization, how crystallization takes place, okay? So if we have, let's say, a polymer in its melt state, okay? And before it's melt, we prepare it in a very thin film, and then we melt it by heating it up and viewing it in an optical microscope. Okay, a very characteristic, very interesting structure, such as these ones. Okay, is formed. Okay, this structure, this spheric structure. Okay, this circular structure are called spherulites. Okay, spherulite, from the Greek word sphera. Okay, sphera, which means circle. Okay, these spherulites usually show what is called a Maltese cross pattern under polarized light. We will see that in a bit. And these form by nucleation at different points in the sample, okay? In order to grow these, we have nucleation at different points in the sample, okay? And then after nucleation takes place, these are formed and then they grow, okay? And they stop growing when we have impingement, okay? So when we have impingement, which is a situation that looks like that, all spherulites touch against each other, and then we don't have any further growth. Let me draw it a bit for you. We go here, okay? So what happens in this case? Here, after T0, we have the polymer melt, okay? There's nothing in there. Our polymer is in a liquid state, okay? Then, by cooling the polymer down, we create this tiny nuclei, okay? So nucleation takes place, and because commonly we said that what happens is that we have a heterogeneous nucleation either due to the presence of foreign bodies or even small things that we cannot absolutely control unless we use very specific let's say conditions, laboratory conditions such as clean rooms. So the presence of any dust or any problems within our equipment can lead to heterogeneous nucleation. 99.9% of the times we will have heterogeneous nucleation, okay? So after that, these essentially these nuclei start growing and they form what we said before. They form the spherulites, okay? And the spherulites show this characteristic Maltese cross pattern. This is called a Maltese cross pattern. These are the spherulites. Sorry. Okay, this is the process where growth takes place. Spherulites, and so the Maltese pattern. Okay. And then at T4, we have impingement. The spherulites grow so much, so they touch against each other and they cannot grow anymore. So in this case, we can have like spherulites looking like that. Okay, Maltese cross. The Maltese cross pattern is observed in a microscope, in a polarized microscope. Under polarized light. The polarized microscope is a bit different compared to the normal microscope, where we have the light, the sample, and the objective. In the polarized microscope, we have the source of light, we have a polarizer, we have our sample, then we have another polarizer, and we have our objective. Okay, because it's ferrolight, so this anisotropy in structure. Okay, if you rotate the polarizer at a certain angle, you'll be able to observe this this very unique structure of the spherulites, which is called the Maltese cross. Okay. Okay, and obviously, in order to do that within a microscope, what do we need? We need to control the temperature very well. And how do we do that? We use what is called a hot stage. Okay. So we have a microscope and a stage where we control temperature accurately. Okay, so the structure essentially looks like that. Light source, polarizer, hot plate and sample. Have the objective and the polarizer here. Don't worry, this is not something I will be asking you to remember for the exam or whatever. It's just just how the experimental setup looks. Let's have a look at the real experimental setup actually. So yeah, these are the spherulites we said, okay, and yeah, crystallites can organize into spherical structures that are called spherulites. Each spherulite contains lambda crystallites, okay, and the anisotropic morphology of the spherulites, as you see, because they have different regions of optical response, okay, leads to the appearance of this characteristic Maltese cross, okay. Yeah, this is a process that we said takes place during the crystallization process. This is the impingement. And this is essentially the setup that I was telling you about. Here we have different elements. Here we have the microscope. This is experimental. For the observation of the spherulites, okay, and the crystallization process in general. Here, the number 5. Let me use color. This is the hot stage, and we control the temperature of the hot stage through this panel here. Okay, this is a liquid nitrogen. We use liquid nitrogen if we want to cool down very fast our material, also in order to induce quenching. And The microscope is connected to this monitor, and you observe these spherulitic structures. Let's have a look. Let me show you how do we observe this in a real life situation. Stop sharing. Let me share my share screen PowerPoint. Okay. Yeah, this is the melt state, and you see how fast we have here. We have nucleation at these small regions, okay, and these continue growing and growing. Okay, we have the formation of spherulites, of characteristic structure of Maltese cross, and they grow and grow until we have impeachment. Okay, until the spherulites touch against each other. You can see that it is not obvious where we can have particles where nucleation is initiated. Okay, so it's not something that we control very actively. Only thing we can control, and it is important to try that in the preparation process when we have nucleating agents, these foreign particles that I was saying, such as fillers, pigments, and so on, is to make an attempt to essentially disperse them as much as we can within the melt. Okay, that is during the preparation process. So you can see that the spherulites grow with each other. Until we observe impeachment. Okay, stop sharing. Let's move to our normal sharing. Where is it? Stop, right? Molly. What about now? Can you hear me, please? Okay, fantastic. Sorry, I've no idea. I've no idea what's happening and why every time we have so many problems. I have no idea. Anyway, let's get back to work. So I was saying that it is. Sorry, guys. It's not my problem. I didn't do anything. It's this software problem. It's what's called Tencent meeting. I hate it, but anyway, it is what it is. So from a structure that's like that, okay, as big as that. This is a polymer. This is polypropylene. Okay, it has a size of microns. Okay, this is polyethylene over there. It doesn't really matter. So this has size of let's say centimeters in length or millimeters, let's say in thickness. Okay, if we melt it and then start crystallizing it, we have spherulites. Okay, so spherulites generally their size is in the order between 50 to 500 microns. Okay, if we look upon the structure of spherulites with let's say very specialized microscopes, what we get is lamellae. Okay, I will explain a bit more about lamellae now. But lamellae, their dimensions are very small. Okay, so if we look upon the thickness of the lamellae, this has dimensions between 20 to 60 nanometers. Okay, so we're going orders of magnitude lower. And then if we look upon the structure of the crystalline, the polymer chain, in this case, what we have is a structure within the angstrom dimensions. So we have, from moving from a polymer sheet to a spherulite to a lamella and then to the polymer chain, we have every time we move across one structure, what's important structure, we go one order of magnitude lower size. One order okay, so we start from millimeters and we go all the way up to angstroms, okay, which is a tiny amount of size. Let's go back to the nodes and let me draw you a bit more. You see my skills in drawing. So what happens if we look with a specialized microscope upon a spherulite? Okay, if we look upon the structure of a spherulite, if we look, let me use black. What happens is that we see something like a special snowflake. Sorry. You know that each snowflake is different, okay? And the same applies for different spherulites. So the spherulites have completely different morphologies, okay? And this is a spherulite, okay? Close up, let's say. If we zoom in upon a certain branch of the spherulite, we zoom here, what we can see, of course, very difficultly, is that we have a region that looks like that. Second region looks like that. Okay, and here we have the crystalline morphologies. Sorry. And between them, these are the crystalline morphologies. And between them, we have the amorphous part, okay, which is chains that are completely entangled and generally no order between them. Okay, so this is the amorphous part, and this is a lamellar structure. Okay, so in terms of dimensions, we go from a continuous polymer sheet then to the growth of spherulites. Okay, and if we look upon spherulites, we saw this lamellar structure. Okay, now something also interesting is that these crystalline parts here, okay, they can have two conformations. Okay. The first conformation is called adjacent reentry, where the chains go in and out of the crystalline parts in the next available position. Okay, so it looks like that, the crystalline part. And here we have okay, so here we have a perfect, let's say, crystalline structure. It's called adjacent reentry model. As you can realize, in order to achieve this or observe this this kind of crystalline structure, it is very difficult. Okay, and because it's very difficult, it is only observed in crystals that are solution grown. Okay, in crystals that we grow very accurately in order to have very high degree of crystallinity, almost perfect crystallinity. Okay, so it is more common in solution grown crystals with perfect crystalline structure. Okay. However, the most common type of crystalline model within this lamellar structure is what we call the switchboard model. If any of you has done any, let's say, robotics or kind of, how are they called? Raspberry type of switchboards, you'll realize these look very similar. Okay, so the switchboard model is that the chains go in and out in random positions with the crystalline regions. Okay. Okay, you can have some order as well, but generally this process is completely random. Okay, so this is the switchboard model. And it's generally, it is the most common model. It is favored in materials where we observe spherulites. Okay, so starting from spherulite here. We have the crystalline morphologies and the amorphous part, that is the lamellar structure. And if we zoom onto the crystalline morphologies, then the crystalline parts can have two conformations. This is the adjacent reentry model. Or the switchboard model, where the chains go randomly in and out in the crystalline region. Okay. Now let's go back to the notes, to the slides. Sorry. Yeah, this is what we said from the spherulite. If we zoom into the spherulite, we can see the crystalline and the amorphous region. This model, how's it called? The adjacent reentry model was essentially proposed in 1957 by Keller, who essentially did this solution ground crystals. And then if we look upon these crystalline regions, we can get the crystalline structure, the polymer chain of our material. Okay. Yeah, this is the crystalline morphology. Polymers are rarely 100% crystalline because, as you realize, we have huge, very long polymer chains. It's almost impossible to get all those chains aligned. Okay, it's very, very difficult process, and that's why we said that the crystallinities general are between 20 and 80%. Okay. Yeah, we talked about that. That strength and modulus often increase with crystallinity. Annealing is a process where essentially when we find this temperature here, where we have maximum growth rate, when we find this temperature here, we keep the polymer at this temperature. Okay, we let's say during cooling we find this polymer, this temperature where we have the maximum growth, and we hold the polymer at this temperature for a certain amount of time. The more we hold the polymer there, the higher degree of crystallinity we will have. Of course, we will not achieve a perfect crystalline, of course, because perfect crystallinity depends on a number of factors, as we said, also to the polydispersity as well. But if we use annealing, which is essentially keeping the temperature of the experiment at this temperature for a certain amount of time, this causes crystalline regions to grow further and crystallinity increases. Okay. Yeah, this is the lamellae and the crystalline regions. Some very interesting patterns. Yeah, lamellar cross, Maltese cross. Again, this is what we saw earlier. This is for isotactic polypropylene. We can have a crystalline lamellae and amorphous phase. And the different types of crystallinity models, the folded lamellar structure or the fringe missile structure. Okay. And yeah, this is for polyethylene. Essentially, if we can fabricate this if we have solution grown. And a very important question now. Let's go back to the notes because I want you to remember that. My notes. Find my notes. Where are they? Yep. Okay. So why do if we ask ourselves, why do polymer chains do this folding process? And why don't they, let's say, align themselves like that? Okay, which is nicer and neater and so on. And they will have they will have, let's say, more significant intermolecular forces and better behavior along one direction. Okay. The reason behind that lies in the competition between the kinetics of the Gibbs free energy or the thermodynamics. Okay, and if we look upon the diagram of the Gibbs free energy, is the Gibbs free energy. We say that you remember that we said that polymers want the minimum Gibbs free energy because it's thermodynamically more stable. Okay, so if we create this graph, here we have the option of, okay, here we are in the melt state. Okay, here we're in the melt state. Here we have the extended chains. Let's say the chains are essentially aligned next to each other but fully extended. And here we have the folded chains. Okay, you can realize that the energy barrier, even though the system likes to have lower Gibbs free energy, the energy barrier for these two systems is higher for the case of extended chains. Okay, so Tg2 is higher than Tg1. That is the energy barrier. So in the case of folded crystals, we said that the process is governed by kinetics. What does that mean? It means that we have fast intermolecular nucleation. Because delta G1 is low. Okay? For the case of the extended chain crystals, this process is governed by thermodynamics. And why is that? It's because you realize that in the case of extended energy, extended crystals, we have significant entropy loss. Okay, the entropy is much lower even compared to the folded crystals. Okay, so we have and in this case we have extremely slow intermolecular nucleation. So delta G2 is high. If we take the example of polyethylene, the energy that we need in order to create extended chain crystals is 280 erg per centimeter cube. Something. Erg is a kind of an old school energy unit. Okay, don't bother too much. I just use it in order to observe the difference between the energy that the system needs in order to create extended energy crystals. And let's have a look at what is the energy for the system that is required in order to create folded crystals. Sorry. Okay, so because of the lower energy barrier, the energy barrier for the folded chain crystals is only 90 erg per cubic centimeter, while in the case of extended chain crystals is 280. So you realize that the system prefers to do something that is fast, and it demands lower energy compared to the putting more energy in order to create these extended chain crystals. Okay, and that is why we say that the process, essentially crystallization, is controlled by kinetics rather than thermodynamics. Okay. Yes, that's what we were saying. Flexible chain polymers do not stretch out until full extension. Instead, they fold back on themselves after stretching. Okay, even if we stretch them sometimes. Okay, if we do not induce a permanent deformation, after that, after stretching, they will form out form this structure. Okay, and of course, as you can realize, different types of polymers with different types of chains so different characteristics in order of stretching them. Okay, you can see that polyamide, or essentially nylon, okay, has these very, very long chains, but the intermolecular interactions between the chains are strong, okay, because the carbonyl, oxygen, and the amide hydrogens form hydrogen bonds. Okay, so once we align them, they form very strong fibers. Okay, we align, formation of strong. The same is for polyethylene terephthalates. It's no point in discussing that. And a bit more detail about crystallization from solution. As I said, in order to have this adjacent reentry model, we want extremely high degrees of crystallinity and very, very precise growth conditions. Okay, and of course, this process is not. It's not, let's say, compatible with industrial techniques. It's only happening because of scientific curiosity, and it can only be prepared in tiny amount of samples. And if we look upon this first observation of single chain crystals, I think those were polyethylene by this Professor Keller. You can see how nicely these are fabricated. Okay, these are observed by TM. Okay, transmission electron microscope. They have a very small thickness in the order of 10 to 20 nanometers, as you can see. Expected theoretically, and these do not form any entanglements. Okay, so because of that, they are able to form this very intricate and very interesting structure. These are other different type of crystals, single crystals again, and these are the two models that we discussed: the adjacent reentry model and the non-adjacent reentry, where we have more common, of course. Where the chains can go in the switchboard, and then they can go out wherever they want. Okay, it's completely random. Yes, that is what we said about the morphology. Discussed about this. And as I said earlier, industries generally prefer to have polymers that crystallize faster. Okay, and because of that, they include nucleating agents. So if we look upon the example of polypropylene, here these are the nucleating agents. Okay, so on the presence of the nucleating agents, we have growth of the nuclei much faster. Okay, crystallization begins much faster. So we have smaller spherulites. Or crystallites, let's say, but faster crystallization. So it is very important, if you want to control the speed of crystallization, it is very important to know that you will make the polymer crystallize faster, but your temperature won't be the ones that the original non-nucleated polymer will be. Okay. And as you can see, this is non-nucleated and non-nucleated, much smaller crystals, and so on. And the same here for IPP plus clay. I will stop here. I will finish this part tomorrow. I took things a bit slow, but I will finish this part tomorrow. We will do also a small revision, multiple choice, unofficial completely, just to help you, point you and direct you towards some of the important parts that we discussed on the thermal transitions. And hopefully tomorrow we will also, not hopefully, we will also go to the next section of our class, which will be on polymer blends and copolymers. Okay, so I took a bit more of your time. Apologies for that. Let me stop sharing. I hope you all have a good evening, and I will see you all tomorrow. Bye now.